So in the last couple of classes, I defined different types of linear combinations of vectors, right? So the first that we saw was this notion of an affine combination, wherein you have a linear combination where the coefficients all sum to 1. They're all real valued, but they have to sum to 1. And that essentially describes, if you take 2 points, then the affine combination essentially describes the line passing through those points. And corresponding to that, we defined the notion of an affine set and the affine hull of a given set. Similarly, now if we put the further restriction that the coefficients should not only sum to 1, but also the coefficient should be non-negative, then what we get is basically the line joining the 2 points, the line segment joining the 2 points, and that's what we call a convex combination of 2 points. And corresponding to that, we had the idea of the convex hull of a given set and also what a convex set is. So a convex set is one which is closed under convex combination. Right. We also define the idea of a conic combination, wherein, again, it's a linear combination of points, but the coefficients are all non-negative. Right. So that's what I call a conic combination. And if a set is closed under conic combinations, or if a set is so corresponding to a conic combination, or we have the idea of a ray, right? Take a given point, look at the set of all alpha times that particular point for all alpha between 0 and infinity. Then this set describes a ray which originates from 0 and then goes all the way up to infinity, passes through that particular point. Right? So if a given set contains all the rays passing through that particular set, then we call it a cone. Right? And if it is closed under all conic combinations, then it's a convex cone. Right? So again, corresponding to a set, we also have the idea of a conic hull of that particular set. Right, so these were sort of 3 different kinds of sets that we saw: affine sets, convex sets, and conic sets. Right, and so later on, I defined this notion of a hyperplane and that of a half space. Right, a hyperplane it's an affine set, but it has a very specific dimension in Rn. A hyperplane is essentially an affine set of dimension n-1, right? And affine dimension n-1, and every hyperplane splits the space Rn into 2 half spaces. So a hyperplane essentially corresponds to the equality A transpose x equal to B, and for A transpose, the set of all points satisfying A transpose x greater than or equal to B forms 1 half space. The set of all x for which A transpose x is less than or equal to B forms another half space. Right? And each of these corresponds to a linear inequality or a constraint which represents a linear inequality. Right? These are all linear constraints. Okay, and if you have finitely many such linear inequalities, then they define what is called a polyhedron. And if the polyhedron is bounded, then we call it a polyhedron. Given a set of linear inequalities, the corresponding constraint set, that is a set which satisfies all those inequalities, may or may not be bounded. Right? And if it is bounded, then we call it a polyhedron. And our goal is to get geometric intuitions for what each of these constraints look like. And we'll also see where these sets and where these kinds of constraints may arise in practice. Okay. So towards the end of the last class, I defined this optimization problem called a linear program. So what is a linear program? A linear program is one where the objective function is a linear function. Essentially, you want to, let's say, maximize or minimize A transpose x for a given vector A. Your variables are basically correspond to the vector x, subject to a bunch of linear inequality constraints. right? So A1 transpose X less than or equal to B1, A2 transpose X less than or equal to B2, and so on. So in this class, let's actually see some examples of linear programs and maybe how to solve them. We're not going to look at algorithms to solve them, but we'll just use a solver to get the solution to these problems. Now, if you recall some of the discussion from the last class and the one before that, we saw that if you have such a linear program, basically you have a linear function, you want to maximize or minimize a linear function, and your constraint set forms a polytope, then the minimizer, or basically the optimizer, is always achieved at some particular vertex, right? Or at least an edge, right? So, and that we'll make use of that fact in one of the problems that we're going to see today, right? So let's start with the following problem, right? So this is a problem that arises in networks. It goes back to sort of the 70s and 80s. And the problem has roots both in computer science as well as in networking. It's called the max flow problem. Okay, so suppose that you're given a communication network, right? So what is a communication network? It consists of a bunch of nodes. Please settle down. So the communication network consists of a bunch of nodes and some links between pairs of nodes. Right? And you can represent this communication network in the form of a graph. It could be something arbitrary. Now let's suppose that we sort of specially designate two of these nodes. One is basically going to be a sender and the other is going to be a receiver. Sometimes it's called a source and a sink. So we have a source and a sink. You can think of this as the sender and the receiver. And the goal is to make sure that the sender has a bunch of packets to send to the receiver. And you want to make sure that as many packets can be sent per unit time as possible to the receiver. So right now, what do the intermediate nodes do? All the intermediate nodes can do is basically forward packets, right? So suppose it gets, let's say, this particular node over here, it can receive packets from, say, this node, and it can send to this node, or potentially it could send from this, or it could receive from this particular node and send packets to this node and this node. Right? But it can only but each node can basically communicate only with its neighbors, no one else. Right? This models networks such as the internet, wireless sensor networks, and so on. Right? And communication potentially can be two ways. So in one particular instant, each node can potentially send packets as well as receive packets. But there's a constraint. So you can't send so each node can't send arbitrarily many packets per unit time. So in each link, we define this notion called a capacity. What is the maximum number of packets that you can send across that particular link per unit time? And there are different ways of abstracting this out. Let's say that for each edge or for each link, I'll give a particular number which defines how many packets can be sent per unit time. Now, this could be in any arbitrary positive real number, right? But for now, let's suppose that let me just arbitrarily fix something. Right? So across this link, you can send one packet per unit time. Across this link, you can send 2 packets per unit time. But I'm not specifying in which way the packets have to go. So for example, maybe this particular node could send 1 packet in 1 unit time. This node could send 1 packet and receive another packet. But the total number of packets that sort of are exchanged in that particular link has to be at most 2. Right? So you can't send 2 packets and receive 2 packets at the same time. But you can send 1 packet and receive 1 packet at the same time. I could also sort of say that in this particular link, it is 1 packet per unit time, but I'll allow a certain relaxation in the sense that I could chop up a packet into fractional packets. Okay, and that's because we're typically averaging across time. So I allow, let's say, sending 0.3 packets and receiving 0.7 packets in 1 unit time. Okay. So that's the problem setup, right? Is this problem setup clear? So for example, one protocol, and the goal, of course, is to design this forwarding scheme. So basically, you have to tell each of these intermediate nodes of whom to send packets to and whom to receive packets from. Right? So one strategy would be the following, right? So the source, you want to know what is the maximum number of packets that can be sent from the source to the receiver, to the sink, right? Now, what you could do, one strategy is that the source sends 1 packet along this particular link. So basically, the source is sending 1 packet to this neighbor, and this neighbor all it does is whatever packet it receives from the source, it just forwards it to this particular node. Similarly, what this node does is whatever it receives from this particular node, it forwards to this particular node, and so on. This forwards to this, right? So you can think of this as sort of one path from the source to the sink, and this as another potential path from the source to the sink. Okay, so per unit time, along each path, I'm going to be sending 1 packet. So I'm not violating the capacity of each particular link. I'm sending only 1 packet across each link per unit time. This may or may not be optimal. I'm just giving one strategy. All right. So overall, what is the maximum number of packets that you're sending per unit time from the source to the sink? Correct. So in this particular strategy,
1/3.
2, right? Because I'm sending 1 packet along this particular link. We're assuming that forwarding is done instantaneously. Okay. So forwarding is done instantaneously, and that is because, of course, there could be a delay. That's okay. But effectively, all you care about is utilization of that particular. You will have multiple packets to be sent from the source to the destination. But yeah, simplification is that forwarding is done instantaneously. So I'm sending 1 packet per unit time across this particular path, and 1 packet per unit time across this particular path. So effectively, the total number of packets I'm sending per unit time from the source is 2. Correct? 1 along this path and another along this particular path. Is that clear? Are there any questions? Is the problem setup clear? Okay, great. What we want to know is, okay, I present a network before you. It would consist of maybe several thousands or millions of nodes, and I give you the capacities of each particular link. What is the maximum number of packets that I can send? Right? This is called the max flow problem, given a particular graph and 2 special nodes, the source and the sink. What is the maximum number of, or what is the sort of, you can think of this as the weight of a particular path. That is, as one of you pointed out, the minimum of all possible weights along this particular path. In this case, it is 1. And similarly, along this particular path, the minimum weight is 1. So the sum of these two, the sum of the weights of these 2 paths is equal to 2. Right? But effectively, what we're looking at is the same networking problem that I just discussed. So this is the forwarding problem. Right? What is the maximum number of packets that can be forwarded per unit time from the sender to the receiver? So let's go ahead. Let's see, can we formulate this as an optimization problem? If so, how do we do it? So firstly, what are our optimization variables? Okay, the flow at each edge. So for each edge, how many possible flows are there? 1, 2, right? One from, let's say, this vertex to this vertex, and another from this vertex to this particular vertex. So right, so the flows so for all I comma j, I have, let's say I have an xij, which is the flow from I to j. Per second. Okay, so this is our variable, optimization variable, right? What do we know about the problem itself? Correct. Let's what do we know about the problem? What is presented to us? The capacities, right? So for each edge I comma j, I have capacities. So let's say for every pair of vertices, I can define a Cij. If there is no edge between some particular pair of vertices, then the capacity is simply equal to 0. So I am given the capacities. So for each pair of vertices I comma j, I have a Cij which is greater than or equal to 0. If Cij equal to 0, it means that there's no edge between the two. And another constraint is that Cij will always be equal to Cji. So in fact, for every edge, you have only one particular number. Not that you can send, say, if Cij equal to 1 and Cji equal to 1, then it doesn't mean that you can send one packet and receive one packet at the same time. But this is how we'll just specify the problem. Okay, specify the capacities. So in other words, I can represent the variables in the form of an n by n matrix, if n is the total number of vertices. Right? So the variables can be represented as a matrix X. And the capacities can be represented in the form of another n by n matrix. Right, so this is what is given to us, and these are the variables. Now, what do we want to maximize? What is the function to be optimized?
Flow leaving source. From source to sink.
Okay, yeah. So you can say that it's the total flow that is leaving the source. Correct? Effectively, what we want is the total flow that is going from the source to the sink, right? But that effectively is the same as the total flow, the sum of the flows which leave the source, or the sum of the flows that arrive at the sink. You can take either of these two.
Need not be the case always, right? Like you can have nodes that need to queue up in between.
So right now we're assuming that that all a node can do is basically forward. It can't store any packets. Whatever is received in one particular instant has to be immediately forward. So it can't say receive 2 packets and send 1 packet. Right? At the same time, it can't, of course, it's not possible to receive 1 packet and send 2 packets. So each node cannot have any memory. That's a constraint that we will explicitly impose on this particular problem. So f of x is, this is our objective. So this is the total flow leaving the source or total flow into the sink. Right? And what is that equal to mathematically? Let's suppose that I have n vertices. I'll always call the first vertex the source, or I'll index everything from 0. So the 0th vertex is always going to be the source, and the n minus 1th vertex is always going to be the sink. So what is this equal to? Right, so it's summation j equal to 1 to n minus 1 xij. Sorry, x0j. Right? Is this clear? All right, so now what are the constraints? Okay, so of course, so along each edge you cannot exceed the capacity. So first constraint is the capacity constraint. So each xij should be less than or equal to cij. What else? Okay, is there something more basic? Sorry? Okay, is there something even more basic? Xij should be greater than or equal to 0.
Would it not be xij plus xji?
All right, that's correct. So it's actually xij plus xji should be less than or equal to cij. So the total flow along both directions should be at most equal to the capacity. You could operate below the capacity of a particular edge, that is fine. And well, you also have non-negativeness constraint, so xij should be greater than or equal to 0 for all I comma j. Can't go negative, that doesn't make sense. Okay, so what is the third constraint? I think one of you already mentioned this. Conservation. So each node can't really sort of store packets. Basically, the total flow arriving at a particular node should be equal to the total flow leaving that particular node. Right? And how do you state that? So for all I, j equal to 0 to n minus 1, j not equal to I. What is the total flow arriving at a particular node? Xji. should be equal to summation j equal to 0 to n minus 1, j not equal to I of xij. So this is the total flow that is leaving a particular node I. Correct? Or I can also put this as a flow conservation constraint, or I can also say that the difference between these two should be equal to 0. Any way you want to put it. Yeah. Correct. So this should hold true for all intermediate nodes. Right? So for all I between 1 and n minus 2, this holds. Any other constraints?
The total flow living is
Okay, that's one way to put it. Or you can say that there's no flow incoming into the source and there's no flow that is leaving the sink. One way to put it explicitly. What circular routing?
intermediate nodes.
Correct. Correct.
Packet forwarding happens among those things, it does not go on.
That's fine, right? So what
Packet will never reach.
correct. So that's why I'm saying that no packet can arrive at the source and no packet can leave the sink.
Intermediate nodes.
But will that happen?
It can happen.
How?
So how you route the total.
Don't these constraints don't take care of that already? Right, because the total flow that comes out of a particular node is equal to the total flow that comes into that particular node. And then explicitly saying that summation overall j equal to 1 to n minus 1 x j0 is equal to 0. The total flow incoming into the source is equal to 0. And the total flow that is leaving the sink n minus 2 x n minus 1 j, this is equal to 0. Right? Any questions? Yeah. This says that the total flow that is going out of the sink is equal to 0. So the sink can't generate any packets and the source cannot accept any packets. Yeah, there are no self loops. So in the capacities, CII is equal to 0. It's given to us. Yeah.
The last condition,
Yeah.
shouldn't it be like individual terms equal to 0?
But I already have a non-negative constraint, right? So it's the same effectively, but I'm just condensing it to one constraint instead of n minus 1 different constraints. right? So just to summarize, our goal is we have this, we are given a particular network, a source and a sink in this particular network, and we want to know what is the maximum number of packets that can be forwarded per unit time from the source to the sink. Along each edge in the network, we are given the capacity of that particular link or that particular edge. And our goal is to find out what is the maximum, or design a forwarding scheme essentially, right? And so in this case, the variables are basically the flows along each edge, that is the number of packets that are going to be sent per unit time from node I to node J. The constraints are specified in terms of the capacities. So for each pair of vertices I comma j, you're given the maximum number of packets that can be sent in either direction for that particular link ij. The objective is you want to find the total, what is the maximum flow that can leave the sink, leave the source or arrive at the sink. So that is basically summation j equal to 1 to n minus 1 x0j. But you could also say this is summation j equal to 0 to n minus 2 of x j n minus 1. So you can take either this objective function or this objective function, doesn't really matter. And the constraints are the following. Firstly, you have the capacity constraint, that is sum of xij and xji should be less than or equal to cij. We want xij to be greater than or equal to 0, so the flow should be non-negative. We also want flow conservation, so the total number of packets arriving at a particular intermediate node should be equal to the total number of packets which leave that particular intermediate node. And the source and the sink, the source cannot accept any packets, the sink cannot generate any packets. Right? So that's the problem, right? So that's the formulation of this particular max flow problem. So now what do we see? What are the constraints and what does the objective function look like? Everything is linear, right? So this is an example of a linear program, right? So in fact, yeah, all right, great. So now can we sort of describe this in terms of just I know that we've written all of these constraints down explicitly, but can we just write it, let's say, in NumPy notation? So remember that my variables, I want to represent it in the form of an n by n matrix. So how do I represent the objective as well as the constraints in terms of, slicing operators, for example? Yeah.
Here the forward path and the reverse path are defined exclusively or
which one?
constraint one?
Correct.
Ki and xi.
Yes.
Will they appear? They will not appear in the
So they don't. So for example, it's not that xij should be less than or equal to cij and xji less than or equal to cji. So for each pair of or each link, you're given a capacity. It doesn't matter how you use the capacity, whether forward or reverse or both. But the total number of packets that can be sent in that particular link, all directions put together, should be at most cij. Exactly, yeah. But then again, for example, I could send 0.3 packets along the forward path, 0.7 packets along the reverse path when the capacity is 1. That's allowed.
But we're trying to maximize data being sent from source sender.
Correct. I'm just saying that it satisfies the constraint. It may not be optimal. That's a different story.
I'm talking about possibility, like when I'm sending from sender to receiver.
Correct.
One path, once it is already utilized.
Yes.
In the optimum path,
Correct.
that reverse path will not exist. Right?
It won't. Yes. but I'm not imposing that as a constraint. You're free to use it as a bidirectional link if you want. I mean, in fact, if you think about it, it's not an optimal way to do it. But potentially there could be an optimal solution. There's always an optimal solution which does not make use of the bidirectional send, sending it in a bidirectional fashion. But there could be a solution which also uses it in a bidirectional fashion. It doesn't do better, but it's allowed. All right, any questions? Okay, so let's sort of formulate this as, in terms of matrix operations. So the variable is X, which is an n by n matrix. Right, so what about the function, the objective? Maximize sum. Great. So it's whatever sum of X right. So the total flow that goes out of the 0th node.
So, this variables, in general formulation, is it implicitly assumed to be a maximization?
No. So I also have to say that I want to maximize this. So it's a maximization problem. This is my objective function, but I can either choose to maximize or minimize. But in this case, I want to maximize. Okay, and let's look at the constraints. So firstly, I have non-negativity. So X is greater than or equal to 0. This is element-wise. Okay, and what else? What about the other constraints? X plus X. Sure, yeah. So I have X plus X transpose should be less than or equal to capacity, and this is again element wise. What else?
Transpose
X transpose of colon comma 1 2 and minus 2.
X of
X transpose.
X
Or X, you can take X also. X of 1 colon and minus 2.
Minus 2, yep.
Comma colon.
we throw
Minus X of 1 1 2 and minus.
Sorry.
so then x of this minus x transpose of this,
Yeah.
and we sum of each row must be 0.
Okay.
Sum of each row must be
Yeah. So X of, so this is okay. So let's sort of interpret each of these terms individually. X of 1 colon n minus 2 colon, right?
Sum over the first, sum over the second axis, like axis 1.
So in this case, I'm only summing over these terms, right? So I have this matrix, X matrix. I'm looking at starting from row 1, I'm going all the way up to row n minus 2, right? So I have a bunch of rows. I'm only for each from this row number 1 onwards, I'm summing row wise. I get basically a column vector, right? What does this tell me? What is this equal to?
Number of connections from one node. No, the capacity, output capacity of each node.
The flow that leaves one particular node, right? Because remember, each is xij. So if I sum over all possible j for a given I, this basically gives me the total flow that goes out of node I, right? So this in fact is going to be a vector consisting of n minus 2 elements, and each element basically gives me the flow that is going out of that particular node. Okay, and this should be equal to the total flow that is incoming into that particular node, right? And what is that equal to?
Extra transpose of the same.
Fine, so I can look at sum of x transpose of 1 to n minus 2 axis equal to 1. Yeah, so so either this is equal to this or the difference should be equal to 0. So the second term basically gives me the total incoming. And we're only going from 1 to n minus 2 because we're only interested in the intermediate nodes, right? Not in the source or the sink. Okay, now if I also have to, any more constraints?
0, colon is 0.
No, not this, right? It's the other way around.
Okay.
Colon comma 0 is equal to 0 and
N minus 1, comma, colon minus 1.
what do you mean colon minus 1?
Till n minus 2, 0 to n minus 2.
Why do you want that?
We don't include the sink for the second sum, right? So for the second summation, okay. Yes.
Because self loops are invalid. Okay, so it's the same set of constraints. I've not changed anything, but I've just written it in a different form right now. All right. Any questions so far?
Diagonal entry 0 is that very trivial or like?
That's part of C. So I'm always going to give a C for which CII equal to 0. Okay. So let's maybe take a concrete example. Try to see what the solution is. It's something which we know what the solution is, and then try to get that solution using a different form. Okay. I'll take the following simple network where I have only 4 vertices. Okay, this is my source. This is my sink. So this is node 0. This is node 3. This is node 1. This is node 2. The capacities are maybe 2, 1, 1, and 1. Let's start with this particular example. So what is the C matrix going to be?
Zero to 1, 0, 0.
0, 2, 1, 0. Two,
0, 0, 1, 1, 0, 1, 1, 1.
1. Yeah. Again, you have to, as a sanity check, this matrix should be symmetric, which is the case. Okay, so this is my capacity matrix for this particular problem. Okay, just take a minute to verify that this is correct. Okay, what should the solution be? Two. Does everyone agree? Yeah. And what would be the optimal solution? So what would be the flows? Can you give me a set of flows for which the max flow is equal to 2?
There could be two solutions.
Yeah,
There could be two solutions.
there could be multiple solutions. That's fine. Yeah.
1, 3, 0.
Yeah. So what is one solution? It is along this edge you have 1. Along this edge you send 1. Send 1. Send 1. Right, this is one solution. Correct. What is another solution?
It could be any real number between 1 and 2.
Correct. Correct. That's true. But can you present just two solutions for that?
2 along.
One
So-
is down, one is on the right.
Correct. So I can send two packets from the source to node 1. One of these packets is sent directly to the sink. The second packet is sent to node 2. And then node 2 basically forwards that one packet to the sink. Okay. Now, note that this is where the sort of assumption of instantaneous forwarding is kind of important, right? Because the total delay or the total path length for each packet is different. There's one packet which takes 2 hops to reach the destination, whereas in this solution there's another packet which takes 3 hops to reach the destination. But we're assuming that instantaneous is being done, forwarding is being done instantaneously, so effectively both packets arrive at the same time. All right. Okay. So now given this, let's see how we would numerically try to come up with this particular solution. So for this, I'm going to introduce a new package called cvxpy. Right. So given an arbitrary convex optimization problem, there are different ways of solving this optimization. Right. In your assignment, you saw one approach, and that was gradient descent. So that is one particular way of numerically solving for this. But for each of these problems, whether it's a linear programming problem or a semi-definite program or anything else, there are already well-known solvers to solve these problems, very efficient solvers. And all of these multiple solvers have been sort of packaged together, and the sort of a front end given to this by this library called cvxpy. So you can specify what kind of a problem you have, what variables you have, what the constraints are, and it will numerically find the solution for you. Right. So let's start with some very basic for now. So how do you invoke this particular library? You just have to import the cvxpy library. You'll first have to install it using Anaconda, for example. And if you want to use it in your code, all you have to do is just start with import cvxpy as something, cp. All right. Now for each part, so let's start with something like very simple. Suppose I just want to minimize x square plus y square, subject to the constraint that maybe x is between 0 and 1 and y is also between 0 and 1. Okay, two simple constraint. We know what should the solution be? So okay, let me just write it down. So I have x square plus y square. This is my objective, f of x square, f of x equal to x square plus y square. Suppose I want to minimize this particular function, subject to the constraints that say x is between maybe minus 1 and 1, and y is between minus 1 and 1. Yeah, so it's 0, 0, right? X square plus y square. What right? Yeah.
F is function of x and y.
Fine. F is a function of x and y. Sorry. Okay. So first I need to declare these two variables. So I can do that by saying when I say x equal to cp dot variable, it sort of instantiates a variable of type this cvxpy. It's a cvxpy variable. So I create new variables, two variables, x and y. All right. So these are my variables. Now, I also want some constraints. And these constraints are typically represented in an array in comma separated fashion. So each of these should represent some inequality, some constraint. And I can specify multiple constraints which are comma separated. So what are the constraints? Okay, so x is greater than or equal to minus 1, x is less than or equal to 1, y is greater than or equal to minus 1, and y is less than or equal to 1. All right. So these are my constraints. Okay. Fairly straightforward. It's kind of intuitive as to how you program this. And now I also need to create an objective function. So for this, there are two things to specify. One is what is your objective function? And the second is what kind of a problem is it? Or do you want to maximize the problem, or do you want to maximize the function or minimize the function? Right? And the library allows you to specify them separately. Now, potentially they could have just given one problem, minimization problem, and depending on whether you want to maximize or minimize, you could either minimize the function or minimize the negative of the function. But here you can specify exactly what you want to do. Okay, so this is, you say cp dot, I want to maximum, I want to, let's say, minimize this function in this case, minimize of, now I need to specify what it is that I want to minimize, right? The function that I'm interested in is x square plus y. Okay, so now I have an objective function, I have a set of constraints, and I have my variables which sort of define, which are used in the constraints. Now I just need to set up the problem itself. Equal to of, well, I have objective and constraints. Yeah, it's fairly natural, the language itself, right? It's exactly as we have sort of built up our approach to solving to sort of defining a convex optimization problem. You define what the constraints are, you define what the objective is, and you set up the problem, and then you just ask the solver to solve. So you just say problem dot solve. Okay, it just says something. Now I want to know what is the solution, right? Sorry? Which one? Yeah, it is. Let's just, yeah, let's see what happens. Oops. Yes. Yes, so the minimum value is 0. And I also want to know what the optimizers are. X dot value. So the optimum value is 0 and the optimizer is 0, 0. Okay. So, okay, let's now choose a different, let's say a different function. Give me something with a different solution. Sorry? Okay, let's maximize. The same thing, but all right, so I'm just changing the objective function, same set of constraints. What should the maximizer be? Two solutions? Okay, what about 1, -1 and -1? So there are 4. Okay, let's see what. Yep. I run into an error. And why is that? What kind of a function? So we are trying to solve a maximization problem for what kind of a function? Yeah, so it's a convex function, and we're trying to maximize a convex function. This does not allow you to do that, right? So there are certain limitations. Well, yeah, it's a bad library in the sense that it helps you solve convex optimization problems only. It's limited. So in fact, more than a library itself, so cvxpy does not really do the optimization on its own. It's kind of a language that allows you to interact with other solvers. It's not a solver in itself. For that, you'll have to use some other solver, which is, I mean, there are a bunch of other solvers. In fact, if you go to right, if I just go search for cvxpy, so go to the cvxpy website, go through all of this. In fact, also, let me see where it was. Yeah,
Somewhere infeasible and unbounded.
correct. There is that, but also yeah, I'm not sure where exactly it was, but it so for each kind of problem, for example, if it's a linear programming problem or a conic optimization problem or a semi-definite programming problem, there are different libraries that are available to solve each of those kinds of problems. cvxpy invokes one of them, all right, and
Discipline, Convex programming, discipline.
yeah, I think somewhere there. Sure. So, in fact, somewhere there's a table which mentions which all are available. And in fact, you can explicitly also specify which solver you want. Some solvers are better than others and so on. Right? But you can't throw any kind of problem and expect it to try to solve this. Right? It has to be a convex optimization problem. You can't, for example, if you want to minimize a particular function, then you have to ensure that the function is convex. If you want to maximize a particular function, then you have to ensure that the function is concave. Anything else, it won't solve. It will say, it will throw up an error. Right?
The boundary tends to.
This is a solution. I agree, right? For this particular problem, there is a valid solution. But cvxpy is not going to give you the solution to this particular problem.
Parameters. In that case, the answer will be in terms of the parameters.
Sorry, I didn't follow.
Example just over here.
Yeah.
It has A and B as parameters.
Okay.
So when we solve it, in that case, we get the answer in terms of
You can get it in terms of parameters.
It's kind of symbolic in that.
Yes, it is symbolic as well. Right? So it's a very powerful library, but you can only solve convex optimization problems using this particular library. So you should know that it is powerful, but you should also know the limitations of these tools. Right? Because in practice, a lot of problems that you will encounter are not convex optimization problems. They're in general non-convex. And you try to solve it using cvxpy, it's not going to really solve it for you. And in fact, cvxpy is not, it's something which allows you to ease into sort of how to solve convex optimization problems. There are other solvers which you can invoke for your particular problem anyway. But this is the easiest way to use a solver and solve a convex optimization problem. Right? Okay, so this is not going to work. Let's take another example. Okay, any other? Just give me another problem. Plus, okay, let's 2 times x times y. Okay, but now let's say I change some of the constraints. Okay, I'll say y is greater than or equal to 1 and y is less than or equal to -1. What happens? Yeah. Why? Is there a solution to this particular problem? No, right? Because this is what constitutes an infeasible set of constraints. There is no point x comma y which satisfies all of these constraints. So let's see what happens. So this is what I give as my specify as my constraints. This is my objective. Right? I specify my objective and yep, I again have a problem. let me just say, okay, so I should have said minus 2x. Right? It doesn't. Right, so you have to be careful in what you feed into this particular solver. You can't give anything arbitrarily and expect it to solve it for you. But as long as you have framed a nice convex optimization problem that can be solved, this will do it for you. Yes, you have to do your own homework before sort of feeding this in. So it's not a general it is fairly general purpose in the sense that it can handle a very wide variety of problems, but you have to make sure that you set it up in this particular framework. All right. Okay. So now, well, right now we have a convex optimization problem, right? Let's take this particular problem. Okay, and let's try to solve this using cvxpy. All right, again, this is still a toy problem because we can solve it by hand, but for example, I could have given a much more complicated looking network, and for that it would not, the solution would not have been so obvious. Okay, so now let's try to set this up. Firstly, I need to define my variables. Right, which is going to be an n by n matrix. I don't have to specify each variable separately. I can in fact just specify the matrix itself as, let me say, n 4 comma 4. So if I want to specify a 4 by 1 vector, all I have to do is call cp.variable 4 comma 1. Okay. All right. So these are my variables. Now I have to define constraints. So firstly, I need to specify my C matrix. I can do this as an NPy or as a NumPy array, for example. Okay, can someone just tell me what the 0, 2, 1, 0,
2011.
2011,
1101.
1101,
0110.
0110, right? Okay, so this is my capacity matrix. Now I want to define my constraints. So first, x should be greater than or equal to 0. So if I just say x greater than or equal to 0, it basically takes this as element wise greater than or equal to 0. That's what this operation does.
If you got variable itself, we can say positive also.
No, so the constraints have to be specified separately. This is sort of, think of it as declaring variables. Which, yeah, you could, but let me specify this separately. Okay, what are the other constraints? X plus I think it's cp dot transpose x should be less than or equal to c. Of what? 1 to n minus, well, n minus 1 because it doesn't take up to n minus 1. Comma colon equal to 1. I could also say equal to some x x 1 1.
Shouldn't it be 1 to n minus
Sorry.
1 to n minus?
So here by default it doesn't go all the way up to, so when I say x of a to b, then it starts from a but goes up to b minus 1. That's Python notation. Okay, what are the other constraints?
X colon
Sum of x colon comma 0 should be equal to 0. Again, you have to be careful. You have to say equal to 0, not just equal to 0. It's a logical operator. X of n minus 1 colon should be equal to 0. These are my constraints. All right. Okay, what is the objective? So I want to maximize something. Cp dot sum x 0 total flow. Right. Okay, this is the problem itself. Equal to oops. Great. So what does it predict the max flow as? 2. Well, there's some floating point stuff, but that's okay. And what is the optimizer equal to in this case? Yep, so let's maybe write it down. So from 0 to 0, it is equal to 0. The optimizer that it predicts is 0. And the next entry is 1.34. And then it is 0.658. 0.66. 0.5 and 1, right? And 0, 1, no, 0.16, 6, 0 and 1. 0, 0, 0, which is obvious. So let's try to see what this looks like. So it says from the source, you send 1.3, this is node 1, node 2. So I say 1.34 packets to node 1 and 0.16 to node 2. From node 1, you send 0.5 packets to node 2 and 1 packet sent to
Points 5.
658. All right, so okay, so it sends 0.5 packets below, but there's also another flow from 2 to 1, which is 0.16.
0.5 from 2 to
0.5 is from 1 to 2, right? So 0.5 flow from 1 to 2, 0.16 flow from 2 to 1. Yeah, so effectively it's, I mean, it would seem that you're sending out 1 plus 0.5, but then it's also receiving 0.16. That's where the missing part is coming from. And you have 1 flow from 2 to 1. It's not the best solution because here you're sort of sending things in a loop. You have 1.34 over here, and you're sending too much and receiving unnecessarily. Effectively, a part of what is being sent over here is being received back. So, but it's still a valid solution, and that's so we'll come to that in a little bit. So remember, the kind of constraints that we've been imposing are constraints of the form are basically linear constraints. Whereas what you are proposing right now is that we constrain the alphabet itself, right? Or the domain, so that it has to be an integer. Can you represent that using any of the, can you represent that as an inequality? Yeah?
Data type can be the
The data type can be an integer, yes. But in general, the problem is that the kind of problems where you only look for integer solutions is different from the set of convex optimization problems, right? What we're doing here is continuous variable optimization. Now, although it may seem that integer variable optimization should be easier to solve than continuous variable optimization, because after all, you're looking at over an infinite state space, whereas now you have just a finite space to optimize over. Getting an efficient solution for the convex optimization problem in fact is easier than getting a solution for most integer programming problems. So in fact, in most cases, if you're presented with such a problem where you want only integer solutions, then your best bet is to relax it to a convex optimization problem where you allow the solutions to be anything you want, and maybe in the end just round it off. Let's see that. Yeah, so I guess it gives the same solution. Probably because it's using the same C. Right? But yeah, if you change the seed, it's going to give you a different solution. So just try to install cvxpy, solve this problem, and just get used to it. There's a lot of documentation available. There's a lot of example code that is available. Just play around with it. Right? It's a good way to just get started. Right? So let's stop here.